functions on the complex plane to something called Bernstein-Sato polynomial, which arises from the algebraic theory of D modules, a pretty, at least recently, in the latter half of the 20th century, pretty active area. I'll also relate this to resolutions of singularities from the algebraic geometry. And hopefully we'll get to see some nice applications to solving partial differential equations, and specifically the existence of Green's functions. Okay. To begin with, I'd like to start with the gamma function. As you may know, the gamma function can be defined as a real integral of the quantity e to the minus t times t to the s minus 1 et. Now, this integral converges and is defined for not just positive real numbers s, but in fact complex numbers s, where as long as the real part of s is positive. So for s that lie in the right half of the complex plane, this is defined. And not only is it defined, but in fact it's a holomorphic function of s. Now, as you may also know, or as you may have heard of, the gamma function has an analytic continuation to the complex plane, or more precisely, meromorphic continuation. So, gamma of s can be continued to pass just the right half of the complex plane, except it will have poles at the non-positive interchange. The question that one of the central questions that I'd like to answer today and use as a springboard for our discussion is, can we replicate this process, but in a more general sense? Can we do this but for not just a power of t, but a power of a polynomial of possibly multiple variables? That is to say, if I have some polynomial in n variables, then can I define the expression f? Now, I'll take f raised to the power s times some nice function. So in this case, e to the minus t took the role of a fast decaying function, which guaranteed that this integral converges, because e to the minus t decays much quicker than t to the s minus 1. In general, I'll impose the strongest condition that I need to make sure that this is always well defined, and I'll explain this in a moment. Now, the first technicality is that for this to even make sense for some values of s, I would like to make sure that f is positive. So I'd like to define f plus the maximum of f and 0. And now I wonder, when is this integral defined? And can we treat this as a holomorphic function of s that can be continued to the complex plane? So when does this have a meromorphic continuation?
Do you want the f's to have only real outputs, or?
Actually, yes. For now, let's take just real outputs, so that this makes sense, I guess. But of course, when we raise s to the complex power, then we're inherently going to have complex values for g. So g will be a complex to complex function. Okay, let's examine the idea of how we can do this for the gamma function. So for the gamma function, gamma of s, let's write this interval again, 0 from 0 to infinity, of e to the minus t, t to the s minus 1 et. The trick is that you can apply integration by parts to this integral. Okay, if you do so, we would like to differentiate, this is e to the minus t. We can differentiate this function, integrate this function, and we get the integral from 0 to infinity of e to the minus t, t to the s, with a 1 over s back. Now, technically there's a boundary term, but the boundary term will actually be 0. Okay, but if you look at this expression, this is nothing but 1 over s times gamma of s. In particular, if you look at small values of, nice values of the gamma function, then gamma of 1 equals 1. And this equation actually tells you that gamma of n is equal to n minus 1 factorial. So the gamma function is the holomorphic function that interpolates the factorials. And sorry,
Gamma of S minus 1.
gamma of s minus 1.
Okay.
S plus 1, sorry. This is gamma of s minus 1. But you can take this equation as a way to define the gamma function on a bigger domain. So we know that this equation holds for gamma of s plus 1. This holds for all gamma with positive real parts. But if we take values of s so that this is defined, so if we take values where the real part of s plus 1 is positive, that is to say, the real part of s is at least minus 1, which is to say that we can take values of s in this extended region, then we can actually define gamma of s to be 1 over s times gamma of s plus 1. And this will agree with our previous definition. So this extends the gamma function to a bigger domain. Of course, it doesn't incur a pole at s equals 0, but that's fine. This defines gamma on this domain with a pole at 0. Now, we can do this inductively as many times as needed, and we can actually define the gamma function on the entire complex domain. So what was the key ingredient in making this trick work? Well, it turns out it's the identity that we have here that made integration by parts work. So what we had was, in fact, if we took t to the s and we differentiated t to the s, then this is equal to s times t to the s minus 1. Or actually, so that the notation is a little bit more consistent with what I'll have for the rest of the talk. I'll index this by s plus 1. We would like to do something like this, but for a general polynomial f. This will require us being able to write something like this. We want to take our polynomial f, raise it to the s plus 1 power, and we want to apply some differentiation operator d, so that we obtain some multiple of f to the s. Now this multiple is going to depend on s. In fact, it's going to be a polynomial of s. So this is what we want to construct for fixed f. Okay, we want to find some differential operator d and b of s. First of all, what is a differential operator? Just to be clear. We will allow this to be some essentially it's a polynomial of s of our real variables x1 and xn, and of our differentiation operators dbx1, dbxn. This will form a ring of differential operators, but it's not a commutative ring because these differentials don't commute with multiplication by x up. Right? But just so that the notation is clear, this will mean, for example, that something like this is the differential operator, and this applied to function f is, well, you differentiate f and then you multiply by xi. And this is markedly different from taking this times xi. The commutator between these two operators is something not zero, but not too bad, actually. Anyway, if we can find some differential operator, then this polynomial is going to be called the Bernstein-Sato polynomial associated to f. Yes, and that's what we would like to be able to find. Okay, any questions so far? I'll take more questions at the end of the talk. But yes.
Does the operator depend only on f, or does it depend also on the actual differential? Sorry, the Bernstein-Sato.
Yeah, so this is a good point. The Bernstein-Sato polynomial and the operator will be constructed out of f. Now, it's not obvious why this would be unique, but it turns out that the set of polynomials that have such an expression is an ideal in the ring of polynomials of one variable. So there's some canonical generator of this. Actually, so let me give you some examples of Bernstein-Sato polynomial. In the case that we just visited, f of x equals x, then if we take just our usual differentiation, the Bernstein-Sato polynomial is s plus 1. It satisfies differentiate x to s plus 1, you get the coefficient of s plus 1. If we take a more interesting example, like f of x1 to xn is x1 squared added to xn squared, then the operator here is the Laplacian. This is sum of b squared dxi squared. And the Bernstein-Sato polynomial that we get here is, I believe, 4 times s plus 1 times s plus n. In general, the Bernstein-Sato polynomial is not easy to compute. Even if you take an innocuous looking case like f of xy equals x squared plus y cubed, I'm not going to write down the differentiation operator, but it turns out that the Bernstein-Sato polynomial is s plus 1 times s plus 5 over 6 plus times s plus 7 over 6. Okay. But it turns out it's a true fact, a theorem that was proven in special cases by Bernstein. So Bernstein, actually, let me write down a statement and then give a little bit of history. Bernstein-Sato polynomial exists for any f, for any polynomial f. Bernstein in 1967 gave an elementary proof of this for polynomials f with some regularity condition on the roots. Actually, he proved much a local, as far as I'm aware, he proved a local version of this, where you can take coefficients in some local ring at any point. And that allowed him to prove what we'll demonstrate today, which is the analytic continuation of complex powers for those polynomials f. I should mention that the main difficulty that arises in proving such a statement is, now if f, the polynomial f, were always positive, then this expression would actually make sense for all complex numbers f's. The problem is that f can have roots, can have zeros. In fact, it's a polynomial of multiple variables, so it can actually have a vanishing locus that's some hypersurface in space. And if you try to integrate around values of x where f vanishes, then this very well might diverge. There's no guarantee that this will converge. So we can't use this expression directly. It also turns out that the more complicated or the more poorly behaved this vanishing locus is, the harder it is to do this explicitly. In some nice cases, such as actually f of x equals x, the fact that it vanishes at 0 doesn't really matter. Okay, but in any case, it took some time for mathematicians to be able to prove this theorem in full generality for any polynomial f. Okay, now it would be helpful for me to introduce some, so where's this? Actually, the other thing I will talk about is distributions. So it'll be helpful for me to introduce the language of distributions because it both simplifies the question a little bit and it will allow us to see how this Bernstein-Sato polynomial will lead to an analytic continuation of this in general. That is, it does nicely express the trick that we applied here, which is integration by parts, which may seem like a one-dimensional thing, but we can extend this to our general setting with the language of distributions. So the way I want to treat this is, okay, so I will place this here. Now, so I alluded to earlier that in this expression, I want to take phi to be a compactly supported smooth function, so that you can integrate phi against any well in this case, this is actually a smooth function as well, except where it hits 0. But you can integrate such nice functions against any locally integrable function. So I'll call this the space of test functions. Let's take an open set of Rn. In general, you could just take this to be Rn, the same thing applies to any open set. This is the space of compactly supported smooth functions of Rn. Yeah, and these are test functions because, for example, we can integrate any f times phi dx for, so if this converges, is defined for any locally integrable function. That's our setting here, at least for values of s with positive real part. This is locally integrable. But if we're to continue this past s in the right half of the complex plane, then we need not be able to define this as a function. In fact, this will be a generalized function, which is called a distribution. A good example of a distribution is the Dirac delta function, which is not a function, but it is a distribution. Because the Dirac delta is, so this is one example. Another example of what I will momentarily introduce as distributions is the Dirac delta function. And if you take this phi of x, the x, this is essentially evaluating the function itself. So, what are distributions in general? What distributions are objects, generalized functions, but they're also objects that you can plug in a test function into. So, if we take space of test functions, and we take the dual of the space, that is the space of linear functionals from this to complex numbers, this is our space of distributions. Now, for those analysts in the room in here, there are some caveats, some technicalities actually to making this definition more precise. One is that it's not just any linear algebraic linear map. It does have to be continuous with respect to the topology you put on here. The topology you put on here is so that a sequence of functions will converge if all of its derivatives converge. But in practice, we don't need to deal with the topology of this very much. And that also gives the topology of this, which is the known as the weak star topology. Anyway, yeah, so what this does is you can think of this as assigning each test function to some f phi dx, which is a linear assignment from test functions to numbers. Now, we can phrase our question, which hopefully I still have over here, as saying, I want to define for each complex number s, g of s, which is a distribution. Okay? This is the object here. And so the question is, in our setting, so g of s, actually g of s is this evaluated at a test function, but I'd like to define our power of f as an assignment for each complex number s, well, so for each complex number s to f plus of s as a function from the complex numbers to the space of distributions. And moreover, I want this to be holomorphic in S. So what does it mean for a distribution valued function on the complex numbers to be holomorphic? Let's define that. So a distribution valued complex function, so a function on the complex numbers, is holomorphic. Let's call this f. Is holomorphic if, well, so f goes from the complex numbers to this basic distributions. And to this basic distributions, we can evaluate any distribution at a test function. That is, if I fix the test function phi, then a distribution evaluates phi to some complex number here. And I need to composite here to be holomorphic for every test function phi. So if phi compose f is holomorphic for any test function phi. That's what it means for a function to be holomorphic. We're not going to have a holomorphic function, but we will have a meromorphic function, which is kind of like, as you would define in complex analysis, f is meromorphic if it is holomorphic at on the complex plane minus some set of poles S, which has no accumulation points. And for each pole, for each singularity, we need this to actually be a pole, which means z minus z0 raised to some power n times f is holomorphic. For some n. So the central question of this talk can be phrased as, do we have a meromorphic continuation of f plus 3s to a distribution valued function on the complex plane? Okay. So as I alluded to, I guess verbally, any locally integrable function is a distribution, just by defining integration against that locally integrable function. But one nice thing about distributions that we will employ is that we can differentiate distributions. This is not something that you can do in general with just functions. If you take a locally integrable function, there's no reason it has to be differentiable at all. But we can define the derivative of a distribution. So let's say we have a distribution f, and it's defined. The distribution is defined by how it acts on test functions, which I'll denote as this inner product f phi. Okay. Now, how do we define? We define some partial derivative of f as a distribution. F is a distribution, its partial derivative is also a distribution. The answer is by integration by parts. Okay, so if we take, I'll write this. The better notation is to use this inner product, but this might be a little bit more familiar if I write this as integrals. So let's write the expression that we want to be true is that df dxi times phi dx is equal to negative of f times d phi dxi. Notice that the boundary term goes to 0 because phi is compactly supported. And also, the derivative of a smooth function is still smooth. It's still smooth and compactly supported. So this is still a nice test function. So this tells us that we can define this distribution, phi, can be taken to be negative of f d phi dxi. That's how you differentiate the distribution. Now, the other operation we can use with distributions, we can multiply it by a smooth function. So the other thing is, if g is smooth and f is a distribution, then we can define the product of g and f. This is not something that will work in a more general setting. The product of distributions is not defined in general. For example, it doesn't make sense to me what the square of the direct delta function is. But if we do have a smooth function, then we can define this by, well, this is just the integral g times f times phi. So that's going to be the same as f applied to g phi. Okay. Now, if we can differentiate the distribution, we can multiply it by a smooth function, then, in fact, what happens is that what I alluded to earlier, which is the ring of differential operators, so here, and so the ring of differential operators, which you will recall has, you can think of this as sums of partial derivatives, but with polynomial coefficients. Now this will act on distributions. That is to say, for any distribution, we can add a differential operator. So if I have a differential operator d, then df makes sense. This is a distribution. Okay. Let's see how we can apply this language to answer our original question, which is how do we extend, given the Bernstein-Sato polynomial, given that we have this key ingredient, which is, I'm going to take it as a black box now, but if you're interested in, say, Bernstein's original proof of the existence of the Bernstein-Sato polynomial, you can talk to me after this talk. I don't think I'll have time to get to that proof, but it is elementary. So, all right. Yes. So, recall that the Bernstein-Sato polynomial is something that gives us, okay, so I'll write this as a differential operator that depends on s. But we have the following expression. This is equal to some, the Bernstein-Sato polynomial times f plus the s. Now, let's stop and realize why this can allow us to extend f plus of s from the right half of the complex line to the entirety of the complex line. Well, if you look at this expression, we could, just like we did for the gamma function, we could take f plus of s to be defined by applying, okay, d of s is a differential operator. And we can apply this to f plus of s plus 1 and divide by d of s. Now, if this has already been defined as distributions, whenever s plus 1 is in the domain of definition, so for example, when s plus 1 has real part plus the real part, then this will define f plus to the s power when s has real part at least minus 1. And we can do this iteratively, getting us from the right half of the complex line to the entire complex line. Now, notice that the language of distributions becomes, in a sense, ever more necessary as we talk about this, because sure, we start with some fairly nice function here, but every time we're taking a distributional derivative. Okay? So we do have to be able to talk about how to apply d to a distribution in general. But it will agree with the notion of f plus to s plus 1 as a function for s in the right half of the complex line. So this does extends f plus to s as a, again, it's a c to d star meromorphic function. So, assuming the existence of the Bernstein-Sato polynomial, this answers our question in the affirmative. And we can actually say a little bit more. The poles that we get when we do this process are, at the first stage, the roots of b of s. Right? So for each, let's say if lambda of 1 lambda k are the roots of b of s, then the poles of this f plus the s are going to be, well, lambda 1, lambda 1 minus 1, lambda 1 minus 2, so on and so forth. Lambda k minus 1, and so on and so forth. I mentioned earlier that the roots of, I think I mentioned earlier that the roots of BFS actually turn out to be negative rational numbers. Maybe I didn't mention this earlier, but it is a fact that it was proven much later, I think in 1990, which actually tells us that all of the poles are non-positive rational numbers, and there's one multiplicity for each number listed here. So it is pretty well behaved. Okay. Yes.
Sorry, can you repeat what you said about multiplicity?
So there's one multiplicity of the poles for each number listed here. There's one multiplicity per term listed in this sequence of sequences.
Okay.
Yes. Okay. Let me sketch a few words as to how this relates to resolution of singularities, which is, so, a little bit of history. This is much more in the realm of algebraic geometry, but in algebraic geometry you deal with varieties, which are, the simplest objects to deal with are varieties, which are, you can think of as the vanishing locus of polynomials. And, you know, some varieties are very nice. They're called smooth varieties. Essentially, they don't have a singularity. They don't look like this. Yeah. But not every variety is of that form. And actually, in our context, you know, the thing of relevance, the variety of relevance is actually the vanishing locus of the polynomial, is f. As I mentioned earlier, the worse this locus behaves, the more singularities it has, the harder it is to prove this theorem. Now, one of a central result in algebraic geometry, which was actually a really difficult theorem to prove, is called Hironaka's desingularization theorem. And that basically tells you that any variety can be desingularized by some process. So any variety here can be turned into some other variety which kind of approximates this variety. I might make a more precise statement, but I'm just going to give some vague words with historical context for now. But any variety can be desingularized, so it can be approximated by a smooth variety, where these two biject everywhere except at the locus of singularities. This is actually a really difficult theorem to prove. It was proven in, I think, the early 1960s. But Michael Atiyah realized around that time that if you apply this theorem, then you can use it as a sledgehammer to solve a lot of technical difficulties that arise in analysis. This is a good example of that. So let's state the version that we want to use. Okay. Yes. So in our context, we'll want. What we're going to do is we'll start with real space, with the vanishing locus of f, and we want to resolve the singularities of f. And when we do this, this process will necessarily turn what started out as real space into generally any real analytic manifold. So a real, if you want an idea of what a real analytic manifold is, basically it's a manifold that has charts with holomorphic transition lines. Okay, so the version of Hironaka's theorem that we want is that if f is real and analytic around 0 in f and Rn. By the way, we'll be doing things locally because even in the context of our problem of defining f plus of s as a distribution on Rn, you can define this locally. If you have some open cover Rn, then if you can define f plus of s as a distribution on each open cover, then you can take a partition of unity, and this will yield f plus of s as a distribution on the entire space. So everything here is phrased locally, but if we have a real analytic function, then for some neighborhood u containing 0, okay, then we can take u and desingularize it. And this will mean the following. So let v of f denote the vanishing locus of f inside U, set of x in U, such that f of x is 0.
Sorry, what is your output space for that?
Complex numbers, I think, is fine.
Okay.
Yeah, real or complex numbers. I don't think it matters too much. Yes. Okay. EFF. Then there exists some real analytic manifold, and a proper map phi from U tilde to U satisfying the following. So first of all, let me define what a proper map is. A proper map is a map such that the pre-image of a compact set is compact. And we'll see how this condition is useful. But first condition is that we want this map to be an isomorphism outside of the vanishing locus of f. So from U tilde, so the restriction of phi to the complement of the vanishing locus of f, U minus the vanishing locus of f, is an isomorphism. And the other thing is that we want the vanishing locus of f to be resolved. One way to phrase this is that if we take f, so f here, let's graph this visually, we have U, we have some manifold U tilde. And this maps to that, and it's an isomorphism almost everywhere. But on a vanishing locus of f, we want this v of f to be resolved. What that means is, what actually turns out is that v of f actually becomes some union of exceptional sets, which will kind of look like hypersurfaces. They're hypersurfaces in correctly chosen coordinates, but let me write down the precise number here. Let's say at each p point in U tilde, there are some local coordinates for our manifold, for our n-dimensional manifold around the point P, such that if we take f as a function of U but pull it back to a function of U tilde, then this takes the following form. It's some invertible function, so some non-vanishing function, which is still real analytic, times powers of 1 like that. And so this means that in these coordinates of y1 to yn, the vanishing locus of f just looks like those hyperplanes. Y1 equals 0, y2 equals 0, etc. And the gist of the idea for why this theorem kills the question that we wanted to answer without going to the Bernstein-Sato polynomial is, now if we want to look at, so let's say we have so our goal is to define f plus of s as a distribution on graph U. Well, what we can do is we can start by defining a distribution on a better manifold. So we can start with a distribution on U tilde, and we can push this forward to a distribution on U. The way that works is, the reason this works is that if we have a distribution on, so let's say f tilde is distribution on U tilde, then we know how to integrate f against any compactly supported function on U tilde, right? So if we want to define the push forward of f well, here we have to understand how to integrate f tilde against some function here, which is a smooth test function u. Okay? And, well, we can pull this back to u tilde. So let's see. I apologize for having both phi and this phi, but they are distinct functions. This phi is a test function on the space u, and this phi is the proper map between u tilde and u. But essentially, we can define this by composition. F by, well, I'm not writing a very precise statement, but you can imagine that if we compose this compactly supporting function on u with this function, then the support of this function becomes some compact set here. And it's still going to be smooth, and so this will define this as a distribution. So start with distribution here, and we can push it forward to distribution on u.
Just to clarify, you shouldn't have star on the right-hand side, right?
That's correct. Yes, this is just f. And, well, the distribution that we want to push forward here is this one, where we're rather complex powers of this function. So if we think about this in the s power. So the question kind of reduces to being able to define epsilon to s times the product of yi to ni raised to the s power as a distribution. But what happens here is that this interval splits. Okay, well, let's ignore the epsilon for now. This can be defined because this interval splits as the product of intervals of y1 to y. And we know how to deal with each of those. Those just look like our gamma function from before. Now, it doesn't split anymore when we have this function epsilon, but that's fine. If we already know how to compute this, then we can put in some non-vanishing function, and this interval will basically still make sense. Like basically, we can still multiply this to phi, just as our language, just as we developed the language of multiplying the smooth function to a distribution. So that's the essential idea of Michael Dia's paper. It's a pretty short paper that you can find, where he made the remark that things from algebraic geometry can really carry over to analysis. And there are active areas of empiric research that kind of deal with this vibe. For example, the subject, I believe, of micro-orbital analysis also seeks to apply tools from algebraic geometry to help you solve, say, PDEs, but on some domain, and that domain might be badly behaved, but the idea is that maybe you can turn this domain into a more well-behaved domain. Okay. In the remaining time, I'd like to get to at least the last thing that I advertised as an application of this, which is Green's function. So, what we're going to work towards is if we have some, it's a thing that has the name of it. I'm not going to pronounce the name, but it's like a Lagrange price theorem, and it states the following. If P is a constant coefficient differential operator, so some constant coefficient polynomial of our partial derivatives, then P has Green's function. What this means is that there's a solution to P of f equals to the right delta. We're always solving this equation in random distributions. The distributions are kind of the complete space in which you can work with things. Notice that the right-hand side is also a distribution. So we want a distributional solution to this equation. And once you have a solution to this equation, you can output a solution to any P of f equals g, basically just by convolving with g. So that's why Green's functions are so widely studied, because if you have a Green's function, then you can solve this PDE in general for anything on the right-hand side. Okay, so let's see if I can quickly sketch how we get here. From our analytic continuation of complex forms. Okay. It will seem perhaps a little bit magical, but in any case, okay. Now, f is going to denote the polynomial again. It's not going to denote this distribution. But let's say, let's start with our polynomial f, which we know has an analytic continuation, or powers of f have an analytic continuation to the complex form. Okay. Now, this polynomial is probably going to have a pole at -1, or this function s is probably going to have a pole at -1. But if it does have a pole, well, any meromorphic function has a Laurent series expansion at any point. So we can take this and take the Laurent expansion around s equals 1 to 1. And what you obtain is the following. You'll have some, okay, let's call it q sub minus n times s plus 1 to minus n plus q sub minus n plus 1 times s plus 1 to minus n plus 1 plus n. Notice that this is a distribution value function, so these coefficients are still going to be distribution value function, but that's fine. These q sub i's are distributions. Now, if we take this equation, so actually, if we take this equation and we multiply by f, I'll drop the subscript f plus f. It really doesn't matter. So f times f to s. Okay, so this is equal to q minus n times f. Notice that we can multiply the distribution by this function f times s plus 1 to minus n plus n. Okay. But now if we evaluate this at s equals -1, this is nothing but 1. This is f to the 0. It's 1. And so the Laurent series expansion over here is going to have to be, well, we can't have any poles. I mean, all of these coefficients. So it's solely equals to this, but this will tell us that q sub I times f is equal to 0 for I less than 0, and q sub 0 times f is equal to 1. Basically, we output 1 by having this be the constant coefficient of s to the 0. And all the coefficients before then have to be 0. And what this tells us is that we have a distributional inverse to f. Okay. Yes, this distribution times f equals 1. Now, I want to point out that 1 over f is not necessarily easy to define as a distribution, because if f has 0, then 1 over f can really blow up quickly, and it can blow up so quickly that you can't necessarily integrate a smooth function against a bounded function against 1 over f. But it turns out that the complex analytic continuation of complex powers actually allows us to find the distributional inverse to any polynomial. Okay, and it seems like a cool result, but how do we, make sense of this in the context that we want to do, that we care about? By the way, the other thing to remark here is that this inverse is not unique, because you could add any linear combination of negative q-dots. So for example, if you take this, something constant times that, this is still a distributional inverse. Okay, it's not unique, but that's fine. There is no ring of distributions, so there's no reason that inverses have to be unique. Anyway, the last step is this. If we have q0 times f equals 1, okay, now I need to temper this distribution a little. It's a small technical step, but basically there's a smaller class of distributions which are dual to a bigger class of functions. Distributions are dual to a space of smooth, compactly supported functions. That's the tightest requirement you can require for distributions. But if I expand the space of functions to functions of fast decay, then its dual is a smaller space of distributions, which are called tempered distributions. But basically, I can twiddle with this and I get a tempered distribution. And a point of this is that those functions those functions that they act on have a Fourier transform, which still lie in the space. Which means that you can define the Fourier transform with tempered distributions as well. Now, the final remark is that if I take the Fourier transform of this expression, let's see what we get. So let's work backwards from here, actually. If we want to solve this, so this is going to look like some linear combination of like d sub d mu xi. So if we want to take this, apply it to f, and we take the Fourier transform of this, then the Fourier transform sends any partial derivative to multiplication by xi. That's what it does to differentiation. It's quite like the Laplace transform as well, but it takes a partial derivative into multiplication by xi. So if you took this equation and you took the Fourier transform, then you would get some. Now these operators instead become multiplication by polynomials. So it's actually multiplication by a polynomial, which let's say ui times f is equal to the Fourier transform of the right delta function, which is 1. So this suggests how you actually get the Green's function here. You take, you work backwards. You take this distributional inverse, make it a tempered distribution, take the Fourier transform, and that should output the distribution that you need for a Green's function. Okay. So there are more things I could talk about here that I didn't have time to talk about, but I think I got to the gist of the story. The main part, there are references that you can find. You can find notes on Bernstein's original proof. You can also read Attia's paper, which is pretty short, 6 pages long. And yeah, I'll open the floor now to any questions.